Okay, YouTube only lets me post 15-minute videos, so I've just had to break up going through these example calculations for conservation of momentum into another video. So we've looked already at the collision example. Now we're going to look at, in this video, an example of how we do conservation of momentum calculations involving an explosion. Okay, let's look at an example explosion question. And I apologise if this is a bit hard to read, but it is quite a good question. I can send you a copy of it if you need, but I think it should be okay once you print it for the notes. So we've got here a stationary object of mass 7 kilograms explodes to form 3 fragments: A, which has a mass of 2 kilograms, B, which has a mass of 1 kilogram, and C, which has a mass of 4 kilograms. The fragments move in the direction shown in the diagram below. A is travelling at a speed of 2 meters per second, B at a speed of V, that's going to be our unknown later on, and C at 2 meters per second. Assume no external forces are acting. Now, the first thing it asks us to do is to state the total final momentum of the fragments after the collision. Now, if we have a stationary object initially, it doesn't have a velocity, therefore an initial total momentum must be equal to 0. And we know from the law of conservation of momentum that the total initial momentum must be equal to the total final momentum, which must be also equal to 0. Now, you don't need to write all this stuff here. Really, all you need to put there is 0, but I'm just making it clear to you this process. What's our total initial momentum? That law of conservation of momentum says total initial momentum equals total final momentum. So if that equals 0, that must equal 0. Part 2. In the space above, draw a clearly labelled diagram showing the vector addition of the final momentum PA, PB and PC of all 3 fragments. So, let's consider these. What is the momentum of A? Well, that's equal to the mass of A times by the velocity of A, which is equal to 2.0 times 2.0, which is equal to 4 kilograms meters per second. The momentum of C is equal to the same, mass of C times velocity of C, which is equal to 8 kilograms meters per second. And C is equal to the mass of, this is B, isn't it? B is equal to the mass of B times by the velocity of V, so that's equal to 1 times VB. Reese, you'll like the VB reference, I'm sure. Okay, so let's do a vector diagram of this. Let's start, just because it's simple. What's the direction of C? It's downwards. So that would be the momentum of C, and that would be equal to 8. The momentum of A, keep it colour coordinated, would be in this direction, and that would be equal to half the length of the first one. I might have drawn that a little bit long, but that's pretty close, which would be equal to 4. Now, we know that the total final momentum is 0, so the momentum of, I might just go to another colour, the momentum of A plus the momentum of B plus the momentum of C must equal 0. So we must get back to where we started at this point here. So the momentum of C must be equal to that. So that's our labelled vector diagram showing the vector addition of the final momentum of the 3 fragments. Then in part 3 we need to solve this for the velocity of fragment B. Now we know from this diagram that this angle here is equal to 60 degrees. This angle here is equal to 90 degrees. That's 60 plus 30. So that angle there must be 30 degrees. So we can use any number of our trig relationships because we know 3 angles, we know the hypotenuse, and we're trying to solve for C. So I might go with sine. The sine of 60 equals the opposite over the hypotenuse, which equals PC over, sorry, I've labelled that wrong. Just a correction, hopefully you picked that up. That should be PB, that's fragment B there, so that should be PB. So opposite is actually equal to PB divided by the hypotenuse, which is PC. We want to know PB, so we times both sides by PC to cancel that out, and we get that PB equals 8 times by sine of 60, which should equal about 6.9 kilograms meters per second. Now that's its momentum. We know that momentum equals mass times velocity. So we want to know the velocity of B. So we divide that by the mass of B. That should be mass of B. Velocity of B divided by equals the momentum of B divided by the mass. So that's that number divided by its mass, which is equal to 1. So we get that VB is equal to 6.9 kilograms meters per second. So we're just dividing the momentum, which we worked out here, by 1. Hopefully by the time we get to year 12, we all know that a number divided by 1 is itself, even if we've been on the VB. Thanks.